Hello everyone, thanks for coming to this Isogeny and its application session. And we have four nice talk, very nice talk, include cover many aspects of Isogeny, including isogenies, assumption reductions, through constructions. And so the first talk will be given by Maria Corte, Rio Santos, and Sam Franklin about an algorithm for efficient detection of splitting and its application to the isogeny problem in dimension 2. Yeah.
Thank you. Today we'll be talking about an algorithm for the efficient detection of NN splittings and how we can apply it to the isogeny problem. Before we begin, we'd just like to say that we acknowledge the traditional owners, the Gadigal people of the Eora Nation, where we are meeting and sharing our work. Okay, so let's get started. There we go. So our motivation lies in isogeny-based cryptography, and the reason why we're interested in this is because it's a type of post-quantum cryptography that has been considered in this standardization process. So the fundamental problem in isogeny is the general isogeny problem. And this asks us to find an isogeny between two supersingular elliptic curves. So this underlies the security of many isogeny-based schemes, most notably ski sign, which is a signature scheme in this for signature schemes, and it has advanced now to round 1. So it's receiving a lot of attention from the community. In this work, we consider the isogeny problem now in dimension 2. So rather looking at elliptic curves, we're looking at their dimension 2 analogs. Isogeny problem we consider to be an upper bound for the security of isogeny-based protocols, where now you're looking at dimension 2 abelian varieties. So the reason why we may be interested in the dimension 2 analogs is that the SIDH attacks show that understanding these higher dimensional isogenies is necessary to understand the isogeny graph of dimension 1. And the algorithms we developed in this paper can help you understand how to navigate these higher dimensional isogeny graphs. Though this is like a very fundamental problem, much is conjectured about it, but little is known. And in this paper, we make the first, a step towards understanding the isogeny problem in higher dimension. Yeah, so in particular, we look at the problem in dimension 2. We look at against this problem due to Costello and Smith, and we decrease the concrete complexity of it. I'll just now introduce some objects that we'll be working with. So to generalize the elliptic curves that we use in dimension 1, we instead consider superspecial abelian surfaces over the same finite field. So there are two types of these surfaces. The first is this reducible type, where your surface is equal to a product of elliptic curves. And if you're considering superspecial abelian surfaces, these elliptic curves are supersingular. So in a way, in this case, dimension 1 problem, because it's just creating dimension 1 objects. Now there's a second type, which is this non-reducible type, where your surface is equal to the Jacobian of the genus 2 curve. Now we're working in isogeny-based cryptography, so we have to look at isogenies. And dimension 2 case, we look at NN isogenies, which generalize the usual N isogenies that you look at in dimension 1, where now instead of being generated by 1 point, it's generated by 2 points, which satisfy a certain technical condition, which just makes sure that these isogenies behave well. So I won't any of these objects, because for the purposes of this talk, we only really need to keep in mind that there are these two types of surface. That's reducible, where you can reduce it to the dimension 1 case, and one that's non-reducible. Okay, so now we can look at the isogeny problem in dimension 2. So in its most general form, it asks us to find an isogeny between superspecial abelian surfaces A and A prime defined over FP squared, where your prime will be of like cryptographic size, so 128 bits. And as in the dimension 1 case, we can look at this problem in a related graph. So let's define this graph. So so P is going to be a cryptographic size prime, and N will be a small odd integer. So our graph will have vertex set being these abelian surfaces up to isomorphism, and the edges are going to be our isogenies. And because we can decompose these abelian surfaces into two types, the vertex set can also be given as a disjoint union of abelian surfaces that are isomorphic to this product. So these lie in this EP set, and those that lie in this JP set, which are just those that are equal to this Jacobian. And the graph looks something like this. So it has around P cubed nodes, this is a finite graph. And around P cubed of these will be JP set, so that they will be non-reducible. But what's crucial to this paper and to the best attack is a special subset of blue nodes around P squared of them that are these reducible nodes. So abelian surfaces that are isomorphic to a product of elliptic curves. Finding this special subset within the main graph is kind of the crux of the Costello-Smith attack, which Sam will now describe.
Okay, so the Costello-Smith attack basically starts with a node, which you might as well take to be one of these non-reducible nodes. And then you want to find a path to a different node, to an isogeny graph. So the first step is just to reduce it to an easier problem. So the idea is just to walk around in the graph, more or less randomly, until you find a product of elliptic curves. So you expect this graph to have very good mixing properties. So if you just take random steps for a while, you hope to hit a product of elliptic curves eventually. That should take about O of P steps, namely because there are O of P cubed nodes in general, and then there are O of P squared products of elliptic curves. And then you solve a much easier problem, the isogeny problem in dimension 1, which should take about big O of square root P time. In fact, you solve it twice, once for E1 and E1 prime, and once for E1, E2 and E2 prime. And then you sort of do some clever patching together argument, which allows you to solve the isogeny problem in dimension 2. Okay, so clearly the bottleneck step here is this walking to a product of elliptic curves, and that's the step which we accelerate now. So very concretely, what does the attack do? You, Costello and Smith, walk around in the 2-2 isogeny graph, to this gamma 2p, and they just walk until they hit a product. So if you start on a node in J of P, one of these irreducible nodes, you take a step via a 2-2 isogeny, and part of just the formulae of 2-2 isogenies, if you compute them, it will just tell you whether or not the image is actually a product of elliptic curves. It just comes out of the formulae, and if it's not, you just do another step. And then you keep repeating until you actually get it. Should take about big O of P time. So a natural question is, while taking steps in gamma 2, could you actually have detected if you were close to a product nearby, but for a different n, maybe for an n greater than 2? And it's not super clear how you might do this. One thing, a very naive idea, would be you could just compute every single n isogeny originating from A naught. But this is extremely costly. Like I'm taking a 2-2 isogeny. That's much cheaper than taking an n isogeny for any other n. So the question is, can you actually do this without computing isogenies? Can you sort of shine a flashlight around the graph nearby and see if you spot a product? So this is what we do. So there's this function alpha. For the experts, it's sort of some normalized version of the Igusa invariance, kind of like the J invariant in dimension 1, which assigns to A uniquely a triple of elements of FP squared, which just pin down A up to isomorphism. And the most important thing to take out of this part of the slide is just some easily computable thing. It takes almost no time at all. It's just a handful of multiplications. And there's this very beautiful paper of Kumar, in which he provides some rational functions which pick out all of the abelian surfaces which are NN isogenous to a product of elliptic curves, just depending on this alpha. So he gives us 3 functions which tell you exactly what the alphas are for NN for abelian surfaces which are NN isogenous to a product. So now the problem is kind of reduced a little bit. It is instead asked you, maybe we can just find some R0 and S0 which solve this set of equations. The first equation being I1 is alpha 1, I2 is alpha 2, I3 is alpha 3, and alpha 1, alpha 2, and alpha 3 are just numbers that you can work out very explicitly very quickly. And so that's what we do. So we take some rational function, fk. This is just the difference. So we want this to be 0 if we want it to be NN split, or we want, more precisely, we want an R0 and an S0, which we can plug into this and make it equal to 0. So to do that, one can just take the numerators of these things and ask them to be 0. And one of the ways you do this is through elimination theory. You compute these so-called resultants, and then we compute the GCD. So we take the resultant of F1 and F2, F2 and F3, and then compute the GCD. And as a bit of an exercise, just to work out that if the degree of this GCD is 0, then A is not NN split. And if it is 0, then it is NN split. So these are some quite concrete calculations. Again, you can bound very, very precisely exactly the number of multiplications required. And actually in the paper, we make a slight improvement upon this. You can really pre-compute these resultants completely generically based upon some input data. And then it's really like you can count exactly the number of multiplications required to do this. Okay, so Maria will talk about the rest of the paper.
Okay, so in our paper, we apply this to the Costello-Smith algorithm. So we apply R and then splitting detection to this algorithm, and it gives quite a nice improvement on the complexity. So to begin with, we have to do a bit of pre-computation. So the problem really here is that if you detect NN splitting, so you will reveal more nodes in the graph. So you'll see whether more nodes in the graph are products of elliptic curves. But doing NN splitting detection costs more multiplications. So really what we want to optimize is finding the N less than or equal to 11 that minimize this cost ratio. So the number of FP multiplications that you have to do over the number of nodes that you reveal in the graph, doing this splitting detection and by walking in the graph, in the 2-2 graph. So for the purposes of this example, we just took N being 2, 3, and 5. So the first step, again, is to take a step in the 2-2 graph. And now we will do our splitting detection. So we do the detection for N equals 2. And in this case, we check 14 nodes, taking into account that we've already checked the node that we came from. So we came from a 2-2 node, so we've already checked that one. And then using the Kumar's map, we can check another 14 nodes in the graph. Then for N equals 3, we can check 40 nodes in the graph. And then for N equals 5, we check 156 nodes in the graph. And in the paper, we give like precise counts for how many nodes you check for every N less than or equal to 11. Yeah, so now we have revealed all these gray nodes in the graph. Note that in the original Costello-Smith attack, we would have only revealed this one new node, that's in orange, whereas using our splitting, we've now covered a larger proportion of the graph for not that higher cost. Okay, but let's act like we didn't find a splitting, so now we take another step in the graph, and we repeat the process again until we find an NN splitting. Okay, so now let's go on to our results. So we implemented and optimized the Costello-Smith attack with and without this NN splitting detection. And we ran this for primes from bit sizes 15 to 1000 until reaching the set number of FP multiplications. Note we couldn't actually solve the problem for these primes because it's a hard problem. And so we just capped the number of FP multiplications. In the paper, we actually solved this problem for smaller primes and said concretely how many FP multiplications it took. But for the purposes of the presentation, I'll just show you the cryptographic size primes. So to determine how much better our algorithms were, we counted the number of nodes that were revealed in the graph and the FP multiplications needed per every node revealed in the graph. And this should help us determine how much better concretely our algorithm is. So here are our results. So for primes of around cryptographic size, so around 150 to 500 bits, we see an improvement of 30 to 80 times, which corresponds to maybe around like 5 bits of improvement. And then for the really large prime of 1000 bits, we see an improvement of 160 times. And here in this column, we give the optimal set that you pre-compute. So for the larger primes, this set is always n equal to 4 and 6. You may also notice that the improvement factor increases as p increases, and that's because our detection does not depend on the size of the prime, it only depends on n. And so as your prime increases, it becomes more and more beneficial to do this detection rather than taking a step, because taking a step does depend on the prime. So it gets more costly as you increase the prime. Okay, so that's it for our talk, and we'll invite any questions. Thank you.
Do anyone have any questions?
I guess the obvious question is how to therefore n equals 0 is for bigger n.
Yeah, so n equals 11, I mean, these equations due to Kumar, they come out of some theory of K3 surfaces and moduli of abelian varieties that it just gets very computationally difficult to actually come up with these equations that Kumar has. I mean, analogous things do exist for n equals 12, 13, 14, 15, 17, and 18 and 24, but those particular functions don't exist in such a nice format. So it's possible that one could do that, but it's probably like a hard maths problem, actually.
Okay, so if someone solves an problem.
Yeah, literally. Yeah.
That's a nice one. Is there, let's say, nice formula for how many neighbors of and then isogenies are there? Like, for example, in the standard case, L isogenes graph is L plus 1, right? Here is, I don't know, n squared or
Yeah, so for n odd, it's like n squared plus 1 times n plus 1, so it's n cubed. For n being even, so when n is when n is prime, it's that. But when n has factors, it's a bit more complicated. But we give it in the paper.
okay.
But for primes, it's n squared plus 1 times n plus 1.
Then let's second the speaker again. Yeah, PDF.
Yeah, so since the next speaker is our chair, I'm going to introduce him. So the next talk is by Yifu Lai. It's about simpler and tighter reduction from D-log to CH for a median group action. And this is trying to work with Stephen Gallagher.
Thanks for the introduction. So in this talk, I will give a brief background on level of screw action and our two main characters, D-log and CDH problem, and the prior result on this content equivalence between these two assumptions. And after talking the contribution on our technical overview, I will introduce two open problems on this topic. So firstly, like group, like G be a group and Mexico E be a set, we say G acts on this set by an action if it has the following two proposition. The first one is identity. The identity in the group acts on any set element. For the convenience for this talk, let's just call this set element as a curve E. Will still be the same curve. And the second requirement is the associativity, which means that if you do two group actions, then this is equivalent to you do the group action first and then do the group action next. And we also further require this group to be abelian, and we further require this action is regular, which means that for any two curves, E1 and E2, there exists a unique group element G such that G E1 equal E2. And we may assume we have a uniform sampling over this group G, and we have a distinguished element E on this Mexico E sets, because if we want to build a crypto system, everyone need to know the starting point to do the group action. The abelian group abelian group action has been proven to be very versatile in doing crypto system, constructing crypto system. It can be used to construct the non-interactive key exchange, and PKC in standard model also uses secure oblivion transfer, and can also be used in the pseudo-random function and the signature family, including linkable ring signature, group signature, and accountable ring signature and blind signature. But the efficiency is still kind of a bottleneck in the development, because we have some exponential time attack. So the parameter set goes to be very large. So to build a crypto system, we need an assumption. So the most well-studied assumption has to be the D-log and the CDH assumptions. The first one is the D-log problem, which also called as group action inverse problem, guide problem, which means that you're given AE and your goal is to recover A. And the other one is the computational diffie-Hellman problem, which means that you are given AE and BE, and your goal is to compute ABE. And this is this CDH problem is the essential problem to prove passive secure of your key exchange scheme. And obviously, if you can solve the D-log problem, you can solve the CDH problem. If you have D-log oracle, you can recover A from AE, and then you do action, then you obtain ABE. So that's how you can see D-log problem is harder than CDH problem. But the question is the reverse true? If you have CDH oracle, can you solve the D-log problem? Luckily, Galbraith, Penny, Smith, and Vicadre, they give a content algorithm that is kind of tweaking the Shor's algorithm. They show that they can solve the log problem with log quantum queries to the perfect CDH oracle in the group size. And by perfect, I means that the CDH oracle is always output the correct answer. But because Shor's algorithm is very sensitive to the error rate, so you cannot really boost this algorithm if amplify the success rate of this algorithm, such that if the CDH oracle only succeeds with like a non-negative chance, like 1 over a polynomial in lambda. So can we still have a reduction to show that CDH is harder than the D-log problem in this case? Luckily,
the Montgomery and Gentry, one of the best paper in Nature 2022, they give an affirming tensor with a reduction using O tilde epsilon to the -21 queries to an imperfect CDH oracle. And as you can see, if we want this reduction to be practical, there's still room for improvement. So our contribution is very simple. We give a full black box reduction with O big O epsilon to the -4 queries to the oracle. And we are using very simple math, just a bunch of string of bounds and use the group definition. So now we are ready to talk about the technical overview. So to start, let's say the oracle has been self-randomized, which means that on the oracle on any inputs, we act to random group element at the front, and then we remove them later. The reason I want to do this is because this will not change the success rate overall, but just we want to make sure that the input is the success rate is independent to the input, so that the success rate independent evenly throughout the input space. So to motivate, let's consider an easy case, which means that, for example, if the error is quite random each time, which means that if the oracle output on output ABE, the correct answer with probability epsilon, and then output a random set element or say random curve with probability 1 minus epsilon, then to amplify the success rate in this case is very easy. You can just by running this oracle multiple times, and because the correct answer has the non-negligible chance, and when the oracle fails, it outputs a random curve, so the majority has to be the correct answer in this case. So Montgomery and Gentry, they consider a more difficult case. They call it as an oracle with structural errors, which means that the oracle output the correct answer with probability epsilon, and the correct answer acts by delta 1 by probability epsilon 1, and delta 2 by probability epsilon 2. And where this delta I is some unknown group element, and we call them as errors or an error term. So in this way, you can see the previous method cannot really amplify this success rate easily because you run the oracle multiple times, and these error terms, this wrong answer will shows up also frequently. And so the high-level idea of Montgomery and Gentry is that they want to modify the oracle. They want to kick out some element out of from the output from the oracle, such that make the oracle into a new oracle, such that the new error terms in this new oracle, they are all in some small subgroup S. Why we care about this? Because the error term now are all in some small subgroup. If we do the quotient group quotient, and this will become the perfect CDH oracle over this quotient group. Then in this case, we can just apply GPSV 18 to solve the D-log and recover for these cosets. And then because this small group, this subgroup is small, so we can just enumerate element in these cosets and test which is the correct answer. In the first step, cos O tilde epsilon to the -16. The second one is built on the previous one with epsilon to the -5, sorry. So the overall cost is epsilon to the -21 in O tilde. And the main idea of Montgomery and Gentry is that they notice that if we fill this oracle as a distribution, then the oracle on input AEBE, they distribute as on input E and ABE. So this is quite easy to verify in this case because by writing down the definitions. So which means that if you got a correct answer, then you put back to run the oracle again, you should obtain the same distribution. So this gives us a hint to kick out some element. If the distribution is not the same, then it is not the correct answer. So Montgomery and Gentry, they do as follow. They run the oracle multiple times, and then you got a bunch of instances. And for every element over the support, we take back as the input again and run together with E, and then run the distribution again. If these two distributions look like the same, then we keep this element over the support. And if not, like they look quite different, then we kick this element out. This actually kind of testing the statistical distance of the distributions. And you do the second step, you kick some element out from your output, and you return the resulting element. You got a new oracle. And every sampling, it takes epsilon to the -8, and the support could be as large as epsilon to the -8. So this step costs epsilon to the -16. It is quite expensive. This is because if you want to distinguish distributions, it is always expensive. So the key idea of our improvement is as follows. We notice that if you output if you got a bunch of instances from the distribution, if there is a large gap in the number of instances, and the heavy elements means that they appear the most frequently above the gap, and they are quite stable, which means that if you run the oracle sufficiently many times, the heavy element above the gap will still be above the gap. So this heavy element will just become like an invariance for this distribution. So the intuition is like this: because there's a large gap, so the last element above the gap and the first element below the gap, they are unlikely to be swapped. So that's why the heavy element is quite stable. So we can fill in as an invariance. So our key idea is as follows. We just we sample distribution and we just observe the heavy elements, and we compare these heavy elements, and that's it. And this can reduce the number of queries significantly by just to O to the epsilon to the -4. It's quite a great improvement. And so it sounds good, but the question is how to find a gap. It's also easy. We run the oracle on any input by t times. T is roughly epsilon to the -3. And then we find a large gap with respect to this parameter. And then we record how many distinct elements before the gap. So then we find this index I here, and then we define the thresholding algorithm to compute the invariance. We run any element on input and on any input, epsilon to the -4 3 times. And then we just return the heaviest I element, the element of appear the most frequently. This will just be the invariance of this distribution. And we can prove that this thresholding algorithm is deterministic and with an overwhelming chance. And we have the same proposition like on input A, E, B, E. The invariance is the same as on input A, B, E, and E. So our safety state is just like follow. We just output we just run the oracle multiplies, and then we compare for every element. For every heavy element, we run as the input again, and we compare if the heavy element they are the same. If they are the same, then we keep the element. If not, we just kick the element out. And we can also prove that the heavy element, this index I, it is in epsilon -1. So it doesn't. So the overall, the algorithm is now epsilon to the -6 is epsilon to the -4. So that's how we can reduce the sampling complexity significantly. And this is the overall trick where we use if the comparison. Montgomery and Gentry, they use sampling method to distinguish the distribution, which is quite expensive. And here we just observe the heavy element and do the thresholding since it becomes determinist method. So the cost is very cheap. Another feature I didn't mention in the slides, that's the new error terms in our new error code, they are immediately a small subgroup. It is quite different to Montgomery and Gentry, this new error term, because there are such sets that generate a small subgroup. So in their case, they have to operate the oracle multipliers to let the error terms act on each other and generate a small subgroup. Then they can invoke GPSV18. Here, because we already a small subgroup, so we can just involve GPSV 18 with cost just constant in epsilon. So that's how the overall cost is epsilon to the -4. And so two open problems on this topic is can we have a quantum boost to this reduction between D log and CD problem? As you can see, except for the last step, we use GPSV, which is a quantum algorithm. What we did here is basically classical. So it's also possible to do some like this distinguished algorithm in the statistical theory, like soda paper or ITCS paper, to accelerate Montgomery and Gentry paper, but this can only like improve to epsilon to the -9. But this approach it does not applicable to our results. So still we don't know if this result can be improved further by using some quantum algorithms. And then can we have another question is can we have a lower bound argument for the best plausible tightness for these two problems to like to have a lower bound for this problem? So that concludes my talks. Do you have any questions?
Any questions?
Thank you. So I really have several of your work.
Sorry, can you repeat again?
So we have several of your
Sorry.
basically for like accurate reduction between CH and Zachary and Mark, the previous one, but also like you can't open child basically. So you reduce the number of people before, right? And then you say that you can't move much better than Q squared, for example. So maybe the representation that's from that, right? Like why you want to do better than Q squared?
I didn't quite try this.
Okay.
We can take it offline.
Okay. The question was it's low on the yeah.
Okay. Lower bound in what circumstance?
So you have e to the 4, right?
Yeah.
But you say you can't do much better than e squared.
We can our result is epsilon to the -4, and we don't know if it is possible to have a result for you mean to our result, our approach, the best plausible is probably epsilon to the -2, you mean?
Yeah. So your abstract, you say you can't do much better than that.
Yes.
You say you show some evidence, but your presentation.
Yeah. That is we show if we want to. It's kind of, but that is our argument is kind of classical. We are using some information theoretical argument to argue that's the best possible for this approach. For our approach, and Montgomery and Gentry's approach is probably epsilon to the -2, but that is kind of it's based on some statistical theory and for classical case. Yeah.
I can speak at that.
Next talk is given by Minji on the scale-up HD group action from two-dimensional isogenies.
This is based on Lawrence work with Nobu and Lawrence technique. So let's start with the basic concept of group action. It has just appeared in the previous talk, so I will not repeat the definition, but we have a slightly different notation. G is a group, S is a set. When the group G is an abelian group, there is a very simple key exchange protocol one can use. Let S be a public parameter, which is a fixed set element. If two parties want to obtain a shared secret, then they can each choose a secret from the group. And then they perform the group action, and then they exchange the resulting set elements. Finally, they perform one more group action with their secret key on the set element they received, then they obtain the shared secret. The first such example using supersingular elliptic curves is Seaside, which was introduced in 2018. This is the first post-quantum non-interactive key exchange. It has small key size and compatible speed among post-quantum candidates. So now let's take a closer look at the Seaside group action. The set is the set of supersingular elliptic curves over Fp. The group is the ideal class group of the imaginary quadratic order Z adjoining square root of negative p. So the action is basically you take an ideal and it acts on a curve and it corresponds to an isogeny. You take the codomain curve as the result of your action. In Seaside, we choose EI to be an n-tuple with entries from negative m to m. By the design of Seaside, one can compute efficiently the action of such ideals on curves where frag Li's are prime ideals of small prime norm in this order. And then we can compute the action of their products on elliptic curves. So in this setting, the tuple EI is the secret key because we will publish the set of prime ideals frag Li's. It's natural to wonder if we can build signatures with this abelian group action used in Seaside. Here is a simple graph isomorphism type of proof of knowledge, which is done by using the following sigma protocol. Suppose E is the secret path from between two supersingular elliptic curves, which is the knowledge we want to prove. And then the prover just take a random walk, go to some other supersingular elliptic curve E prime, and the verifier challenges with 0 or 1. And then the prover responds with either the path from EA to E prime, or the path from E0 to E prime, which is the composition of the secret and R. In the context of Seaside group action, as I mentioned earlier, the secrets are n-tuples. So the paths A and R are n-tuples. And what about the composition? It's another n-tuple, but the entries are now in a different rank. 2m now is from negative 2m to 2m. This simple sigma protocol leaks the secret information because if the composition starts with 2m as its first entry, then the adversary knows immediately that the secret has m as its first entry because only m plus m equals to 2m. So CFISH is another construction that tries to fix this issue in this simple sigma protocol. The intuition is that this sigma protocol will be secure if one can compute directly the action of G to the E acting on the curve, where G is a generator of the ideal class group and little e is an integer modulo the group size. But here are two issues. The first one is that it is hard to find the generator of an ideal class group. It takes sub-exponential time on a classical computer. And the second issue is that direct computation of G to the E acting on a curve is not efficient because the exponent E is usually very large. So what's the strategy of CFISH towards solving this problem? their strategy is divided into offline phase and online phase. Offline, they first actually just find the generator of the ideal class group. They did it for P as in C side 5112, where 5112 means the bit size of the prime P. There is no trick in doing this. They just use, and this is a record-breaking class group computation in the literature. And then they compute a lattice, so-called a lattice of relations. This involves solving discrete logs in the ideal class group. Finally, they do a lattice reduction step. And the online phase is first, they solve a CVP problem with respect to this lattice reduction. That way, they have equivalence of ideals. Originally, we have G to the E, and now we have its equivalent to the product of frac Li to Ei's power, with Ei's being small. This is something going on in terms of the definition of the ideal class group. You can take this as a black box. And then finally, we actually do the action. Instead of directly using G to the E acting on the curve, we can now use the product of frac Li's, which is by design efficient. So this strategy turns C-side group action into an effective group action, which is an EGA for short, but it does not scale. Because as we can see already in the first step of the offline stage, this is a record-breaking computation, and we have no way to push this further. So in the following two slides, I will motivate you why we care about EGAs and why we care about the scalability of this strategy. Benefits of an EGA compared with REGA. Here, REGA is short for restricted effective group action. So this is a table credit to Yifu Lai. On the very last right of the table, we have many constructions which will be far from practical that you can build with abelian group action, but if you don't have an EGA. So that includes signatures, as I just mentioned, OPRF, threshold signature, linkable ring signature, efficient group signature, blind signature, VRF generic proof systems. So as you can see, there are a lot more things we can do with an EGR in group action. So that provides enough motivation to construct EGRs. By the way, one example of REGR is C-side group action, the original one. The desire to scale. Why do we want to scale the strategy of C-fish? That's because of the security concern on C-side. So the security of C-side is closely related to the group action computational Diffie-Hellman problem, which is quantumly equivalent to the vectorization problem, according to the previous slide, previous talk, where the vectorization problem was called as the group action inversion problem. There is a sub-exponential time quantum algorithm to solve the vectorization problem for abelian groups. This is an abelian hidden shift problem, and one can use Kupperberg's algorithm. Since 2019, a series of papers studied quantum security of C-side, leaving whether C-side 512 and C-side 1024 achieve NIST level 1 security under doubt. So even probably 1024 would not be enough. And so therefore we cannot stay with just 5112. So it is really important to construct EGAs that can scale. One way to approach this problem is to look at the underlying group action of C-side. It's actually a special case of a more general group action that's in supersingular isogeny theory. So this is the general orientation induced group action, which was first formalized by Kolo and Kohel in 2020. This action looks like the following. So we have the group, which is the ideal class group of a general imaginary quadratic order, no longer need to look like that, look like the C-side one. And the set is the set of O-oriented supersingular elliptic, where the orientation is defined by some endomorphism on the elliptic curve, which we denote by theta. If we take O, the order, to be z square root of negative p, then that's the C-side setting. And theta, why it doesn't appear in C-side? Because it's the natural Frobenius on curves defined over Fp. So everybody knows how that acts, so we don't need to specify it. That's exactly the motivation of scallop, which was a PKC paper last year. So the main idea is the ideal class group is actually easy to compute for orders of the form z adjoining square root of f times, z adjoining f times square root of negative d, with d being a small positive integer. Here's a quick summary of scallop. It follows the overall strategy proposed by CFish, as we saw earlier, and it resolves the scaling issue faced by CFish because it uses a different imaginary quadratic order. For security reasons, f is chosen to be a large prime. There is a trade-off between choosing f so that there is an efficient representation of this anamorphism or having a smoother class number, which is helpful for solving the discrete log problem. Because this trade-off, scallop still has its own scaling bottleneck. It favors having an efficient representation of theta, so they don't have much control on the class group size, which makes the discrete log problem take so long time in their offline phase. Here's a quick recap of what we have achieved so far in isogeny trying to build efficient and scalable EGAs. We start with C-side, which is just an REGA. And then we have CFish, which is an EGA, and it only scales to C-side 5112. Then we have scallop. It uses a different order, different set elements, and it's also an EGA. It scales to C-side 1024. Here, by using the C-side parameter to measure the scalability of scallop, the underlying logic is we are comparing the size of the class group they are using. Finally, as a little spoiler, scallop HD, which is a construction from our work, uses the same imaginary quadratic order and same set elements. It's also an EGA. About its scalability, let's save it to the end. So the motivation of scallop HD is that we may be able to come up a better way to represent the orientation data. This was motivated from the new isogeny representation after SIDH attacks. The technical details are as following. So let phi prime be A isogenies and psi prime be B isogenies for integers A, B that satisfy the commutative diagram. If we define F from product E2 times E1 prime to E1 times E2 prime by this matrix form, then F is a degree D isogeny between abelian surfaces with D equals to A plus B. If we further require that the kernel of phi and psi intersects trivially, then kernel of F is given by the evaluation of phi and psi on the D torsion of E1. So the upshot is that an isogeny can be represented by its evaluation on torsion points, which can be something that has nothing to do with its degree. A priori, we only know how to represent isogeny by its kernel. And with this viewpoint, if we now look back at the SIDH key exchange protocol, it exactly gives a commutative diagram to us, and it exactly reveals the torsion points information. So basically, it gives away immediately the secret isogeny it's trying to hide. So that's why it's broken now. And in our work, we take the idea of that isogeny representation and we apply it on orientations or equivalently on anamorphisms. So here is a definition that we introduce. You can forget about all the details, but just look at the green tuple, which consists of E, the curve, omega beta, two quadratic order elements, which are used to build the commutative diagram that appeared on the previous slide, PQ, torsion basis that we're interested in, omega EP, the evaluation of torsion basis. So they together, we can evaluate the orientation. And this is called a 2D representation of E iota. Here, E iota is just same as E theta that I wrote earlier. And in our paper, we show that let O be an imaginary quadratic order of discriminant congruent to 5 mod 8, then any oriented elliptic curve in SOP admits a 2D representation. So the motivation or the main idea is to use the 2D representation to represent theta in E comma theta instead of using kernel representation. Benefits, we have much simpler group action compared with the one in Scallop, but I didn't talk much about this. See more details in the paper if you're interested. And we don't have any restriction on F coming from obtaining an efficient representation for the orientation. So we can choose F so that the class number is smooth. And then we can use Pauli-Kalman algorithm to solve the discrete log problems very efficiently. This way, we overcome the scaling bottleneck of Scallop. So now the scalability of Scallop HD entirely depends on the efficiency of lattice algorithms. As I mentioned earlier, if you remember, we have a lattice reduction step and we have a CVP step. Finally, implementation and performance of our protocol. So in terms of scalability, which I saved to the end, we managed to scale to C-side 4096. So it's much bigger than the previous ones. There's a tiny issue is that while we completed all the 3 stages in the offline, we haven't finished generating a starting curve for the bigger parameter set due to the lack of sufficiently general genus 2 isogeny library. So it's a very recent research area, and there are still some works to be done. But there is nothing to worry about because in theory, everything is polynomial. About performance, here is a table for the bit size for our important parameters, among which n is the number of L ideals we choose for each security level. And it also corresponds to the lattice dimension we are working with. And this is speed. So as you can see from the table, Scallop HD looks slower than Scallop. That's because we implemented this in SageMath, while Scallop is implemented in C++. We expect that if we also implement Scallop HD in for example, C++ or Rust, we will have compatible or even faster speed. Okay, that concludes my talk. Thank you.
We have time for one question.
Like, I guess that's how the offline is. I don't know if this is true or not, that is.
It's polynomial time with quantum computers, but with wax. So yeah.
Yeah, we have time for another question. One question is about if you don't do the, if you have Scallop HD, if you don't do the lattice actions, how much was the time to run one to actions?
So if we use a different order to do C-side type of things, then we want the exponents to be between -5 to 5 for 512 parameter. But in our results, our exponents are like from maybe -10 to 10. So we're like twice as slow with this step. But this turns REGA into an EGA. That's the benefit.
Sorry, so let's send into again. Next talk will be given by Robbie Peterson on new proof system and or PRF from Seaside.
Thank you very much. Thanks all for attending this talk. So the goal of this research was basically to come up with more flexible proof systems, so a new toolbox to generate proofs for more complex statements in Seaside. And it's an application we presented in OPRF. So yeah, as the two previous speakers have already pointed out, we can describe Seaside as a group action, where we have some commutative group that's also free, that acts freely and transitively on some set of elliptic curves E, but it's star group action. And basically the hard problem related to these kind of group actions is that if I'm given E prime and E, it's hard to find A. And I'm just going to make it simple, I'm just going to call these elements elliptic curves, and A, I'm going to call them isogenies. And we have this compatibility property. So basically, if you apply two group actions consecutively, it's the same as applying the multiplication of the two elements on E. And assume we know the class group. So assume we are in the case where we have EGA, as Vijay pointed out. Then we assume this is also cyclic, so we have a generator for this. Then we can change the description of this group action to this bracket notation, where basically we're acting with some element A in the exponent of the generator. So if I say I'm acting with A, actually I'm taking the generator of A and then apply this to E. So for this, we need to be able to reduce these isogenies to like efficiently divisible elements. So we need to have the class group and the short relation lengths, which we assume to be the case throughout this talk. And here, this consecutive action of elements, since we're working in the exponent group, becomes an addition. And this is what I would call addition throughout this talk. And really, the basic idea of what we wanted to explore in this paper was to look at other arithmetic operations than only addition. So addition is everything we had so far in the Seaside setting. But we wanted to look at multiplication, exponentiation, and polynomial evaluation. And so I'm distinguishing scalar multiplication from multiplication by the fact that we assume in scalar multiplication that one of these two elements, A and B, would be public, and multiplication is when both are private. And just as a quick recap, so we have this ID protocol in Seaside where we want to prove that we have two elliptic curves, E0 and E1, and we want to prove that there's A connecting them, and that we know this A. And here's the associated language to this. And the idea is very simple. We do this similar to a Schnorr protocol. So basically, we sample some random element V, we walk some random path, like we walk a path defined by this element to some other curve, send this as a commitment to the verifier, and then the verifier samples the binary challenge and sends it back. And now we compute a response. For this response, if C is 0, basically we disclose B, so we want to show that we compute this commitment correctly. And if C is 1, then we want to show that we know the path that you want to be B. So if we can respond to both of these things, we can extract A, so we know A. And so we send this response to the verifier, and the verifier checks if this is correct. So this is the standard ID protocol. So how can we turn this into an addition? So we use the same protocol, and basically addition would imply we also want to prove that there's a second curve pair where we use the same A. So why is this addition? So basically it's saying the A that we added to B0 is the same as the A we added to F0. So adding, remember that consecutive applications here is the same thing as addition. And to do this, it's also quite straightforward. So we use the same B. We did the commitment on F0, and we use the same response. And then if the verifier can check that either the left-hand side or the right-hand side is correct, and is also the same for both, then the verifier is convinced that both use the same A. And we can turn this into scalar multiplication just by simply scaling both of these diagrams by some factors. Let's call them M and N. And now we can prove that basically one curve is connected by MA while the other curve is connected by this NA. And basically we can do this by using the multiplication in the commitment phase and again in the response phase. And it's very important to see here that the prover and verifier both need to know M and N, otherwise they can't do it because they need it in the first step here and in the final step here. So this is scalar multiplication, but for multiplication, it's a bit more complicated. Yeah, so now we define this language here. So we've used two diagrams, but we can generally do this, like extend this to k elements. So we also have these languages that are for, let's say we have k pairs of curves and they're connected by the same element or by different multiples of the same element. And the languages that we defined in our work are now exponentiation and multiplication. So exponentiation basically means if I have some element a committed to some curve, I'm giving you a curve that's a to the e, where e is some known exponent, public exponent, or multiplication where I have two curves a, e, and be, and I'm showing you that I'm going to convince you that my new curve is this multiplication of a times b. And of course, with great language comes great hardness assumption. And we looked at the hardness assumptions related to these statements. And of course, addition and scalar multiplication are equivalent, but we could also show that distributed exponentiation and multiplication are actually equivalent, and that they're harder than addition and scalar multiplication. And finally, of course, on the end of the spectrum is always key recovery, which allows us to do everything. So how do I prove that? So here, given these, so I assume, I forgot to put this on the slide, I assume that these two elements are given somehow. And now I want to convince you that the curve I'm giving it to you is AB applied to some base curve. So how do I do this? Well, actually, the idea is to use masking. So what we do is we generate two random elements, X and Y, and we mask A and B. And alpha and beta can now be public elements. So what we can do is we just plug this in, and then basically we use distributivity, and we get 4 consecutive applications. Remember that additions are the same as consecutive applications. So since X and Y are private, because I keep them private, I can just disclose alpha and beta. They hide basically everything else. So this is public. So this step is easily verifiable. And if I look at the next part, I have alpha Y. So alpha is public again, and Y is private. So this is exactly an instance of what I showed to you before as the scalar, as an instance of this scalar multiplication. And the same with beta X. So beta again is public, X is private. So we also can prove this using a scalar multiplication. But now the question is, what do we do about this term? Because this term is again a multiplication, but with 2 elements that are actually private. So what we can do here is we use a trusted setup. So we assume we have a trusted setup that generates an X and Y, sends this to the prover, and it also computes these 3 curves and publishes them. So everybody can access these 3 curves. So the verifier knows that these 3 curves are computed correctly, and the prover can, for any A and B, use this trusted setup. And then we basically plug in these 3 curves. For this last part, we just use NZ, and for the other curves in the proofs, we use also the trusted curves. And the verifier can then verify these 2 scalar proofs and can also verify alpha and beta using these curves. So that's good, but we can do better. So a way to improve this is to use MPC ahead. So now we assume we have this trusted setup, and instead of using the scalar proofs, the trusted setup now generates X, Y, and Z for n times, where the sum of all these xi is x, yi is y, and zi is x times y. And we also again need 2 curves. And now the idea is the prover uses this trusted setup to compute alpha and beta in the same way as before. And then we run an n-party protocol in the head. So the idea is that every party in the head kind of gets alpha and beta, but it also gets these elements x, y, and z. Everybody gets the relative one to them, to their position. And then we input E0. And then every party basically computes this distributed sum that we had before using their shares of this tool. And so this at the end, so the last party, because this is all additive, this last element is exactly A times B E0 if this is done correctly. And what the prover then does is it commits to all of these views. And then the verifier can challenge one of these views, let's say the second one, let's say the challenge is 2, then the prover opens all of the other views, and the verifier can check if they're done correctly. And if they're done correctly, the verifier has confidence 1/n that this is also correct. So, and thus can the prover can convince the verifier with a specific probability of the correctness of the statement. So this is nice, again, but we still have the trusted setup. So how do we get rid of the trusted setup? Well, basically, we can use a technique called cut and choose. So we do kind of a similar thing as MPC in the head part, but also in the first phase. So the prover generates a bunch of these tuples itself. And again, verify can now challenge the prover saying, okay, I want to see everything except 3. The prover opens and then verify again has some confidence that that they are all correctly computed, and especially has some confidence that T3 is correctly computed. And T3 is then used as an input to this MPC in the head thing, and then we repeat. And again, then we have this MPC in the head phase, the prover commits, and the verifier challenges. And so there's like a particular trade-off between these two, like the size of M and N, and also the number of things that we disclose or not, that we can use to really optimize this protocol. So how optimal is it? So remember the first ID protocol that I showed you. I'm going to put this here as a reference. So here, prove and verify cost is, because it's a binary protocol, we need lambda repetitions for lambda as a security parameter. If we look at scalar multiplication and addition, which have the same cost for, let's say, 2 elements, the way I showed it to you before, this cost is just 2 lambda because we run 2 of these proofs in parallel using the same commitment and the same response. If we look at multiplication, we remember in the naive case, we just use 2 scalar multiplication proofs. So it's basically twice the cost. This is the case with the trusted setup. I haven't talked about exponentiation because the time is not enough, but exponentiation is way, way worse because it scales with the logarithm of the side of the exponent. Because we need to do kind of a square and multiply approach. If you use MPC in the head, this strongly proves, especially in the exponentiation case, we get something below 2 lambda, but in the multiplication case, we get something that's close to 2 lambda as well. So this is competitive with scalar multiplication, but we still have the trusted setup. If you want to remove the trusted setup, this becomes a bit more expensive because we also have to prove that the trusted tuples are correctly computed, or the non-trusted tuples in this case, and then we get something 4 to 5 lambda or 3.5 lambda in the exponentiation case. And this is still, it's more expensive, but it's still in the realm of usability. So another question is, why do we do all of this? Well, if you look at these kind of statements, our motivation was, DLog has this really powerful tool which is called pairings. And pairings really allows you to build very, very complex protocols that we don't have in the Isogenies set. And I'm not going to claim that we kind of solve the problem of pairings because you don't have any way to combine elliptic curves in some meaningful sense. But what we can do is we can prove statements of these kind of types. So we can still have a prover running proofs that look similar to pairings. So it's kind of reminiscent of this idea. And that's what we wanted to do. And one of the things we did in the paper is also to use these pairing verified signature schemes and see and basically translate them to the Isogenies setting. This works, but they're not compatible with like the state-of-the-art signature. But it's just like interesting from the point of view. But we, of course, we had to come up with a really good like protocol or application. And what we came up with is an OPRF. And the OPRF works pretty simply. I'm not going to go into details here, but basically we have a server that has a polynomial on its side. So the key is polynomial coefficients up to some degree. And the client has some message. And these are all elements of this group that we're working with. And the idea is that the client simply masks its message, sends it to the server masks its polynomial coefficients, and sends some evaluation of some curve plus the masked coefficients to the client. And then the client can use this and runs its part of the computation, and the output is just a polynomial evaluation of the message. And because everything is masked, the client doesn't learn anything about the polynomials, coefficients, and the server doesn't learn anything about the message. So we have some conditions on F for this to work. One of them is that the degree of F is 2, which I'll come back to shortly. But of course, we also want F to be uniform and collision resistant. This is just to make it a pseudo-random function, of course. And one of the ways to do this is, for example, to use permutation polynomials. And permutation polynomials have degree 3 in the setting, but we can also heuristically argue that degree 2 is enough. The only thing we also have to assume is that we have this kind of new security assumption. So which is basically a one more game. So kind of the unforgeability game of OPRFs. So it's if I can interact with the server in an oracle way, can I come up with a new pair of a message that I haven't queried, and can I find the evaluation of this? And if you listen about the Yifu swap, this is basically the condition why we have to have degree F bigger than 1, because if this is linear, this is exactly the oracle that we can use to extract the secret. So this is the instance of a hidden subgroup problem. And yeah, we can use Shor's algorithm to solve it. But if you read F is 2, then this is not a hidden subgroup anymore, and we don't have this problem. Okay, let's finally look at the computational costs, or like the comparison of our OPRF with the state of the art. So there have been 2 OPRFs in the CSAT setting before. And basically, so one is done by a group from Austria, which has quite a good cost. And the other one is done by Monet, Kog, and Wu. And if you compare them, basically the top one has a much lower cost, but has a much higher number of rounds. But the top one also doesn't need any trusted setup or class for the class group knowledge, but the other one does. And also both of them are not malicious, and don't allow for a malicious client. But the second one has come up with like a version of malicious clients, but then it increases the number of rounds to 4, and it even increases further the cost. So in comparison, our OPRF for 2 different degrees has a malicious client basically for free. The protocol is round optimal, has very, very low computation costs, so not scaling with lambda, and also has very low communication costs, also not scaling with lambda. The thing is, we also need a trusted setup and we need the class group knowledge, but the trusted setup, we can also remove it using OT techniques. And if you like interact with the same server multiple times, we can even use OT extension techniques to make this viable. And another thing that we achieved is to make this verifiable. So this is also the first verifiable OPRF in the CSAT setting. We're still around optimal in the verifiable case, but then of course the computation and communication costs increase, but they're competitive with the non-verifiable case on the state of the art. And that's it. Thank you very much.
Questions? Anyone?
Yeah. Yeah, so that's very hard to compare because that's kind of with something like the masked seaside setting. So there's no direct comparison because it's hard to compare the security level of seaside with this setting. So like we couldn't really conceivably find the correct parameters to compare them to. So we did like a remark in the paper. We can compare the communication costs. So if you go for seaside 496, which is kind of a conservative approach to assume for this level 1, then we're better in terms of communication cost. But then we have the scalability problem that Minji talked about before. So yeah, it's kind of a strange trade-off. But computational cost-wise, we don't know because the master paper also doesn't really go into the details there. And like computation costs in terms of isogenies, they're computed completely differently in the SIDH setting and the CSAT setting. So there's no, we should all implement it and test it, but we can't implement it for these high parameter sets because they don't exist yet. So sorry? The cost of? Each exclusion. Yeah. You mean the cost per round, basically? Yeah. No, I don't know because the thing is, so this formula is it's a formula with like 3 binary coefficients. So it's kind of like some optimum somewhere, but like you would have to see the exact M and N parameters and so on to be able to see that. So yeah, I don't know this by heart. Yeah, it's a good question. I don't know how many rounds. I should check that too.